Good day to you, students. How are you doing? Today we'll be dealing with chapter 13.1, light. Let's deal with the reflection and the refraction of light. Let's start. Reflection of light. We are going to be defining the reflection of light by dragging the following words into the correct boxes. Light usually travels in a straight line. It changes direction when it hits a shining surface or travels from one material to another. All right? The change in the direction of light at any shining surface, such as a mirror, is called reflection. Reflection can be demonstrated with the use of a ray box or a laser. The light produced by a laser comes out in a narrow beam. Let's check. That is correct. Let's move on. Reflection of light also. We are also to deal with the missing words. We are to fill them in. Modern mirrors give clear images. Mirrors' work is based on the laws of reflection, which says that the incident ray, the reflected, and the normal at the point of incidence all lies on the same, what do you think over there? Plane, and on the same surface. For the law of reflection also, the angle of incidence is equal to the angle of reflection. The laws of reflection also works for curved surfaces such as concave or convex mirrors. Let's check. All are correct. Okay, image is formed by a plane mirror. When an object is reflected in a plane mirror, its image is the same size as the object, B, the same distance behind the mirror as the object is in front of it, C, is left, right, inverted, and D, it is virtual. So let's deal with ray diagram, also by filling in the missing words. These are diagrams used to predict the positions of images in a mirror, or when lenses and other optical devices are being used. To draw these ray diagrams, the position of the observer, okay, observer is marked, and then the rays are extrapolated back to show where they appear to be coming from. Let's check. That's also correct. Now, let's deal with the refraction of light. We'll be dragging the words also into the correct boxes to give it a full meaning via its what? Definition. The bending of rays of light when they travel from one material to another is called refraction. There are so many effects caused by refraction of light. Some examples are the sparkling of diamonds, the ways our eye lens produces an image of the world around us, and the twinkling of the stars in the night sky. The broken stick effect is another consequence of refraction. Let's check. That's correct. Now, we are to fill in the missing words. Let's start. When demonstrating the refraction of the ray of light, notice the following conditions. That is, the ray bends towards the normal when entering into the first medium, and the ray bends towards the normal when leaving the second medium. In reflection, angles are defined relative to the normal. Incident ray strikes the block. The angle of incidence, that is what will be there, is measured from the ray to the normal. Now, refraction is still known as the bending of light as it passes through a medium to another. But when the light is perpendicular, that is, it is at 90 degrees to the boundary between the two materials, there is no bending. Let's check. That's correct. So we are also to explain refraction and refractive index. Let's start. Light travels fastest in a vacuum. Another word for vacuum is space, and almost as fast in air. Light travels slowly in glass, water, and other transparent substances. When a ray of light passes from air to glass, it slows down and bends towards the normal. The quantity that describes how much light is slowed down is the refractive index. Let's check. That is correct. So, with this, we define Snell's law by filling in the missing words. The law that relates the size of the angle of incidence to the angle of refraction is known as Snell's law. All right, the greater the refractive index, the more a ray is bent. Snell's law is written as M equals to sine I over sine R. That is the ratio of angle of incidence to that of the angle of refraction. So we check. Oops! Here you have Snell's law. What really happened there was that the L attached to the law ought to be in what? Small letter. Let's continue. Now, let's deal with this question that we see here. Okay? Now, the speed of light in a block of glass is found to be 1.98 times 10 raised to power 8 meters per second. We are to calculate the refractive index of glass. Now, refractive index is equal to what? Speed of light in a vacuum over speed of light in glass. So speed of light in vacuum is always denoted by what? C. While speed of light in glass, we can use any letter to represent it. Let's say X. And what is the value of this C? Light travels through vacuum at the rate of 3.0 times 10 raised to power 8 meter per seconds. Let's divide it by X. Our X now is what? 1.98 times 10 raised to power 8 meter per second. So we have to look for what? The refractive index. The refractive index now, this will cancel this. 3.0 over 1.98. That is what we have left. And we have our answer to what? 1.51. So let's pick 1.51 and check. Correct. So this is the breakdown, the summary of what I just did. You can go through it to understand it better. Let's move on. Another question. A solution of sugar in water is found to have a refractive index of 1.38. You have to calculate the speed of light in the solution. Now, this is what happens. Refractive index, just like I mentioned earlier, is what? Speed of light in vacuum, which I denoted with C, divided by what? Speed of light in solution of sugar and water. So let me represent that with letter X. So we are to look for the speed of light in the solution, which is our what? X. X now, by way of what? Rearrangement or change of subject or formula is equal to X is equal to C over the refractive index. That will be what? 3.0 times 10 raised to power what? 8 meter per what? Seconds divided by what? 1.38. Our X now, that is the speed of light in the solution, becomes 2.174 times 10 raised to power 8 meters per seconds. So do we have it? We have 2.17 times 10 raised to power 8 meters per second. Let's pick it and check. That's correct. So you can see here the breakdown of solution also. So therefore the speed of light in the solution is 2.174 times 10 raised by 8 meter per second. Now, what causes refraction when light travels from air to glass? Option A, the frequency of the light wave changes. That's wrong. The amplitude of the light wave changes for option B. That is wrong. The color of the light changes. No, that is not acceptable. The speed of the light changes. Yes. When waves or light is moving from one medium to another, the speed of the light will change depending on what? The medium. That is our answer. So pick it and check. That's correct. Now, let's deal with our correct statement before we wrap it up for today. Let's look at statement A. The law of refraction states that the incident ray, the reflected ray, are the point of incidence and the normal, all lies on the same plane and on the same surface. This statement is false. Why? Because this statement deals with the law of reflection, not the law of refraction. So with this, if I needed to define this statement, it would have been the law of reflection states that the incident ray, the reflected ray, are the point of incidence and the normal, all lies on the same plane and on the same surface. So we are looking at the first statement, it is what? False. The second statement now, the ratio of the sign of the incidence angle to the sign of the refracted angle is known as the Snell's law. That is correct. That is typically what we also refer to as what? The refractive index. Alright, that statement is perfect and correct. Let's look at the third one. The frequency of light wave changes when light travels from a vacuum of air to glass because refraction. That statement is false. Instead of frequency, speed will have been the best and the good option. So the statement in itself is false. So the second statement is correct. Let's take it and check. That is it. We've come to the end of this class. But do not forget to check our website www.edubbey.com for more of our interactive notes and videos. We also want you to subscribe, and subscribe. Bye for now.